Welcome back dear all for the second session on the flexible collectors. I should remind you here is that the content on these slides I have used I are prepared with the help of the book on the RS Kurmi, as well as I had taken some content from the Google. I would refer you to refer the book of Theory of Machines by R.S. Kurmi, because the content in this book are very good, concise and arranged properly, and for the Mumbai University syllabus. So most of the questions in the university examination comes from the book of R.S. Kurmi. That's why I refer you to prepare the this chapter from Theory of Machines by R.S. Kurmi book. Velocity of the belt drive is given as the length of the belt that passes over the driver in 1 minute is given as pi d1 into n1. Similarly, the length of the belt that passes over the follower or the driven pulley within 1 minute is given as pi d2 into n2. As the belt is same, the same belt is passing over the driving pulley as well as over the driven pulley. So both the equations pi d1 n1 and d2 n2 both are same. So equating both equations here. Now velocity ratio. So velocity ratio, it comes to n2 upon n1 is equal to d1 upon d2, as pi gets cancelled, and what will remain is n2 upon n1 equal to d1 upon d2. That is called as velocity ratio or speed ratio. And when the thickness of the belt is to be considered, then the diameter is slightly increased by the amount of thickness of the belt. So the left hand side is same n2 upon n1, but on the right hand side you have to add the tension, the thickness of the belt in the diameter of the driving pulley as well as in the diameter of the driven pulley. D1 is the diameter of the driver, D2 is the diameter of the follower, and N1 and N2 are the corresponding speeds of the driver and driven shaft, as we had discussed earlier. The velocity ratio of the compound belt drive. Up to here we had seen of the single belt drive system. Now what is the velocity ratio of the compound belt drive system? It is very simple. So velocity ratio between the first driver and the first driven, that is pulley 1 and pulley 2, we can get it as n2 upon n1 is equal to d1 upon d2 over here. Similarly, the second pulley and the third pulley are compounded over here. They are mounted on the same shaft. So the speed of the driving pulley and the speed of the pulley number 2 and pulley number 3 both are same, as we know. So this pulley number 3 will drive pulley number 4. So between the pulley number 3 and pulley number 4, the speed ratio can be given as n2 upon n3 equal to d3 upon d4. So multiplying equation 1 and equation 2, what you'll get is here. Multiply the equation 1 and 2. So as we know, n2 and n3 both are same because they are mounted on the same shaft. So n2 and n3 will get cancelled, and what will remain is n4 upon n1 is equal to d1 into d3 divided by d2 by d4. So if number of pulleys are increased, that is, instead of two coupled system, there are three compound drives, that is pulley 1 drives pulley 2, 2 and 3 mounted on the same shaft, 3 drives 4, and 4 and 5, pulley number 4 and pulley number 5 are mounted on the same shaft, and pulley number 5 drives pulley number 6. In that case, the speed ratio we can get between the last driven shaft or last driven pulley to the first driving pulley, that will be like this. So similarly, we can obtain the relation for 6 pulleys, 8 pulleys, and so on. Now length of an open belt drive. I had earlier shared with you on the WhatsApp group the length of open belt drive derivation. So the relation we get from that derivation is length of the belt is equal to pi r1 plus r2 plus 2x plus under bracket r1 minus r2 bracket square divided by x. So r1 and r2, these are the radius of the pulleys. R1 is the radius of larger pulley, R2 is the radius of smaller pulley. and x is the center distance between two shafts or center distance between two pulleys. So here some may take R1 as the radius of smaller pulley, or they may take as R1 as radius of larger pulley. In both cases we will get the same answers, so it doesn't matter whether you take R1 as radius of driving pulley or the driven pulley. Here one thing you should remember here is R1 minus R2, it's bracket square. Don't take it as R1 square minus R2 square. So you should remember this part. Length of a cross belt drive. So length of the cross belt drive, it's a derivation I also shared you on the WhatsApp. It's a link I had shared you on the WhatsApp. You should practice that derivation. Here the derivation, length of the belt L is given as pi R1 plus R2 plus 2x plus R1 plus R2 bracket square. So R1 is the radius of one pulley, R2 is the radius of other pulley, and x is the center distance between the two shafts or center distance between the two pulleys. So here again you can take as R1 either radius of driver pulley or driven pulley. In both cases you will get the same answer, that is the length of the belt. Now power transmitted by a belt. So power transmitted by a belt is given by P is equal to T1 minus T2 into V, where T1 is tension on the tight side, T2 is tension on the slack side, and V is the velocity of the belt which is running over these pulleys. And always you should remember that the answer we get from this equation is in terms of watts only. So if you have to use it in kilowatts, or in some question it may be given it may be given in the given data that the power transmitted is kilowatt. So you should remember that the power to be used in this formula is in watts only. The velocity of the belt is in meter per second only, and the tension on the tight side and the slack side, it has to be taken in Newton only. So you should remember the units of all three, that is power, tension and velocity. The velocity of the belt, we know the velocity of a rotating object about some center is given as V is equal to R omega. We had seen earlier in the chapter number 2. So omega is equal to 2 pi n upon 60. Again we know this, that omega is 2 pi n upon 60, where pi is a constant, n is the speed of rotating object in RPM, omega is the angular velocity. So we can rewrite this equation as V is equal to R, and instead of omega 2 pi n upon 60, so we will get this equation. So finally we will get the velocity of the belt is equal to pi d n upon 60. Here 2r, 2 into radius, we can represent it as the diameter of the pulley. So it is pi d n upon 60 velocity of the belt. Either you can calculate velocity of the belt from the driving pulley or the driven pulley. In both cases you will get the same velocity of the belt. Ratio of the driving tensions for the flat belt drive. So what is first thing we need to know, what is driving tensions? So here is the tight side of the belt, this one is the driving pulley, this one is the driven pulley, this one is the tight side. So the tension on the tight side is represented as T1 here. Similarly the tension on the slack side is represented at T2 over here. We already know that. So here observe, this is the T2 and this one is T1. So you can take either a smaller pulley or the larger pulley. It's a derivation I will share with you, or it's a link I will share with you on the WhatsApp. So the ratio of the driving tension, that is T1 upon T2, it finally comes at to T1 upon T2 is equal to E raised to mu theta, where mu is coefficient of friction. We already know its notation. So coefficient of friction between the belt and the pulley is represented by mu, and theta is angle of flap. Theta is angle of lap. So first thing what we need to understand is what is angle of lap. So just observe here, just observe please. Here you can observe on this pulley from A to B. Just observe here, from A to B, the belt is in contact with the pulley. Here belt is passing from the slack side to the pulley, and here it releases the pulley on the tight side. So from A to B, if we join with the center of the pulley, that is O to A and O to B, so this angle made between A O B, this is called as angle of lap. That is the angle traced by the belt at the center of the pulley, that is called as angle of lap. It may be less than 180 degrees or it may be more than 180 degrees. And one thing you should remember, the units, that is T1 is tension and T2 is also tension, so their unit must be in newtons. Mu is coefficient of friction, and you already know that it's unitless quantity, and theta is angle of lap. So theta, its angle must be in radians, as theta is out of trigonometric function over here. So whenever an angle is out of trigonometric function in any equations, most of the time you have to take it in terms of radians instead of taking in degrees. So you have to convert the angle. If you have the angle of lap in terms of degrees, you have to convert it into radians first. Now limiting ratio of driving tensions for V belt, earlier we have seen over here. So this is only for the flat belt, that is T1 upon T2 is equal to e raised to mu theta, whereas in case of the V belt drive or V belt system, we already know that its shape of the cross section of the belt, and the similarly the shape of the cross section of the pulley, it is trapezoidal shape, and it is somewhat, its shape is somewhat like V. So the included angle between the two inclined sides of the pulley, or included angle between the two inclined sides of the belt, this included angle is represented as 2 beta. Just here its representation is represented over here, it is 2 beta over here, you can observe. So this angle, it ranges from 30 degree to 40 degree, we had seen earlier. Mu is the coefficient of friction between the belt and the sides of the glue. So it comes up to 2.3 log to the log T1 upon T2 equal to mu theta cosec beta. We can again represent it as T1 upon T2 is equal to e raised to mu theta cosec beta. So we had rearranged only these both equations, this one and this one, both equations are same. Only what we had done is we had rearranged this equation in terms of exponential function e. So T1 upon T2 both are tensions, that's why that must be taken in newtons. Mu is the coefficient of friction and it is unitless quantity. This theta, so theta is angle of lap, we had seen in the earlier slide. So this angle of lap theta, it must be in radians, we had seen earlier. Cosec beta, as beta is inside trigonometric function over here, cosec is a trigonometric function and beta is inside the trigonometric function, that's why you have to take beta in degrees only. So you need to remember that theta is in radians and beta is in terms of degrees only. So you should remember the difference between both, because most of the time the students get confused between the angles and angle included angle and the angle of lap, and they do some mistakes. Now determination of angle of contact theta for open belt drive. The same equation you will get for V belt drive as well as the flat belt drive. It is one of the most important things in case of a belt drive system when we are going to calculate the tension or the power or the velocity of the belt, whichever is asked in the question. So determination of angle of contact theta is almost, you have to do it in every question. So you need to remember how to determine the angle of contact theta or angle of lap theta in both the cases, that is flat belt as well as the V belt. So Sin alpha is equal to r1 minus r2 divided by x. You had seen this equation in the derivation of the length of the flat belt. So sin alpha is equal to r1 minus r2 upon x. r1 is the radius of larger pulley, r2 is the radius of smaller pulley, and x is the center distance between both the shaft, and alpha. So just observe here what is alpha. Just observe here, this is the angle of flap theta, and between FKH over here you can observe FKH, between the points FKH there is angle of flap, and these lines F is joined with O2 and O2 is joined with H. So these lines makes an angle with respect to the vertical axis y axis. The angle between both the lines is called as alpha. Here again you can calculate the alpha, you can understand what is alpha. So alpha is the angle between the vertical line which is passing through the center of the pulley and the line EO1 and O2G. So at both sides you can calculate alpha here. So mathematically you can calculate alpha by r1 minus r2 divided by x. In case of open belt drive, you should remember that this is only applicable for open belt drive. In case of cross belt drive, you have different equation. This belt drive can be either flat belt or V belt. In both cases the same equation is applicable, that is sin alpha equal to r1 minus r2 divided by x. Then to calculate theta, you can observe here, just observe here how much is theta. So the angle made between the vertical line at the center here up to here is 180 degrees. So to calculate theta, that is theta is this much, on the above side there is alpha, on the lower side there is alpha. So to calculate theta, what you have to do is total angle is 180 minus alpha on the upper side and alpha on the lower side. So 180 minus 2 alpha. So it is 180 minus 2 alpha, and to convert it into radians we can multiply it with the help of pi by 180. So because theta is always required in terms of radians. Now determination of angle of flap for cross belt drive. So here again it is very similar. Sin alpha is r1 plus r2 upon x. So you can observe here alpha is here is alpha. So the angle of flap is from E, J to G here. You can observe here from E, J to G there is angle of flap, and alpha is the angle between EO1G and the vertical line. So on the upper side there is alpha, on the lower side there is alpha. Similarly you can get the same alpha over here between FO to H, and there is completely angle of flap over here. So this angle of flap, and this is the vertical line. So the angle made with respect to the vertical line is alpha. So either on the larger pulley or on the smaller pulley you can calculate easily how much is alpha with the help of this formula. Sin alpha is equal to r1 plus r2 divided by x. And angle of flap, in the flat belt it is 180 minus 2 alpha. In case of cross belt it is 180 plus 2 alpha. So here you can observe the angle here is 180 and plus alpha on the top and plus alpha at the bottom, either on the smaller pulley or on the larger pulley. You can understand both will be same. So it is 180 plus 2 alpha, and you can multiply by pi by 180 to get the angle of flap in terms of radians. So similarly, to compare both, I had arranged both here. In case of open belt drive, what is the difference between the equation in case of cross belt drive? So only difference you will get here in terms of sin alpha, and in case of open belt and cross belt is here minus sign in the open belt and plus sign in the cross belt, remaining is same. Similarly, in the difference between the angle of flap in open belt, here is minus and here is plus. So you should not get confused whether it is open belt or cross belt. Depending upon which type of belt is mentioned in the question, you have to use the respective formula. One thing you should remember and note down is that whenever it is mentioned that there is a cross belt drive, then to calculate angle of flap you have to use sin alpha and theta, this equation. But if nothing is mentioned in the question that whether it is open belt or cross belt drive, then you must remember that by default it is open belt only. By default it is open belt drive unless it is mentioned that it is a cross belt drive. So you should always remember this. So in both cases the diagrams, it is open belt drive diagram and is cross belt drive diagram. Thank you for today. We will continue in the next lecture. One thing I should remind here is that the book I had the notes and book I had used for the preparation of these slides are Theory of Machines by R.S. Khurmi, and most of the content in this slide is taken from the book, that is Theory of Machines by R.S. Khurmi. I had used this because in case in Mumbai University's syllabus and the question paper pattern, most of the questions have been asked from the Theory of Machines by R.S. Khurmi. So I would refer you to refer only the book of R.S. Khurmi for preparation for your examination. Thank you all of you.